So difficult you gave up? All people who've done this, raise their hands. That's what I did in 1976, 77 when Douglas McFadden, who taught rendering techniques in this room, but did not teach perspective, unfortunately, he simply told us to buy this book and read it. That's when I bought this book and attempted to read it. I attempted several times and bogged down and gave up. Did that a number of times over the years. It's difficult. It's the subject that artists often not only don't like but avoid to their detriment. There's a solution to this problem of complexity, and that is you take it one simple thing at a time. The same way you learned how to read and write. There was a time when B was dangerously similar to D. And it took quite a bit of analysis and looking and understanding and practice to get it right. You do it that way in learning perspective. You have to learn the letters one at a time, and eventually it will click together. It yields to study. Now, why use perspective? What is the point of perspective? It comes from a Latin word, perspecta, which means to look through. And there's only one reason why you need to know perspective. It has to do with the kind of drawing that I teach, which is that you are trying to trick the viewer's eye into seeing a third dimension when there is no third dimension there to be seen. You are trying to create an optical illusion. This is illusionary drawing. Everybody knows what that is. That's a triangle. But you know, if I go like this and then frame it up like so, it may be that that's a road, right? I've just created an optical illusion. You know, I could put little railroad tracks here, have people standing, and have trees in there. What you do when you look at that, you play this game. We play a game of pretend. That is further away than that, and yet it isn't. They are both on a chalkboard and they are on a flat plane, and yet we play this game. That's further away than this. There's a reason why it works. It conforms to a law, the law of diminution, which I'll talk about, the law of convergence. And then the rule is parallel lines. Lines like that, when they go away in space, look like they touch on the horizon line. That's the rule that conforms to the law of diminution and convergence. So when I do that, I get away with this little game we play to make that optical illusion. The reason you use perspective, the reason we spend the time studying these laws and these rules, is so that we can play this trick. See this flat piece of paper? It's not flat. It's a window into a three-dimensional world. Now I'm going to give you a simplified introduction here. One of the problems of studying any new discipline is defining terms. When I tried to take anatomy and physiology or biology, whatever it was called here, one summer in 76 or 77, I remember the teacher said, this is a beginning class. He said, if there's anything that I say that you don't understand, feel free to raise your hand, feel free to interrupt me, and I'll explain it a little better. And I thought, good, I like teachers like this. And within 10 minutes, I realized that if I were to raise my hand and ask for an explanation of what I didn't understand, we wouldn't have gotten past his first 6 sentences, and he's about 600 sentences into it, because I didn't understand anything he was talking about. I didn't understand those terms. He was throwing out all these terms that he was assuming that we knew, and I didn't know. And I know I've done that in here. You have to do it. You have to have every discipline has to have a private language to make it so that the lay people admire us more. We have to have these specific terms, so we need to define them. And if you learn these terms and get to know them real well so that you don't even have to think about them, it will help you in the coming lectures. Term number 1. You've got to know this to understand perspective. Right angle. What is a right angle? This is a right angle, more or less. Squared up. What's another word for a right angle? Perpendicular. And perpendicular is often used in these textbooks. You should know perpendicular just means right angle, which there was another technical engineer's term for how many degrees. How many degrees is a right angle? Where does that 90 degrees come from? It comes from the idea, you've seen these protractor things. What is a protractor? Oh, it's half a circle. We've got to decide somewhere. Somebody looked at a circle and said, why don't we divide up a circle? Why don't we divide it up into equal little increments? And somebody chose 360 increments so that you can start 360 all the way around, which means that half is 180, which means that 1/4 is 90, and that's where you get, there's 90 little points from there to there. So when you say a 90-degree angle, you're talking about this, squared up. So that makes it easy to know that that's a 45-degree angle, right? And a 15-degree is right there, and a 30 is right there. We will come back to this protractor business quite a bit when we get to ellipses. Okay, 90-degree angle, squared up, right angle, perpendicular. Remember that one. Okay, now, how about parallel? There's two L's, first two L's, just one L at the end. Well, these two L's are parallel to each other. That might be one way to remember it. All right? Two lines that are never going to intersect. They'll go infinitely and they'll never touch each other. And if you tip one just a little bit, you go down far enough and it's going to intersect the other one. All right, what does this word mean? Oblique. Not quite spherical? No. From an angle. What angle?
Viewed from an angle, not dead on.
But what angle? Viewed from a 90-degree angle? Oblique is anything that isn't parallel or right angle. It's everything else. That's an oblique line, that's an oblique angle, that's an oblique, oh, that's a right angle! That's an oblique angle, that's an oblique angle. And of course, to make it oblique, it's got to oblique to what? If you've got a line like that, that's your reference standard, then that means that's going to be oblique, that's going to be, that's a right angle somewhere in there. That's oblique, that's oblique. But see, I might have a line like that as my reference angle, and that's oblique to it, even though it's parallel to the floor, right? And at right angles to a vertical, so you have to have a reference. Oblique means anything that is not at a right angle or parallel. Okay, two other words here that we are related to each other. Obtuse. What's an obtuse angle? Anything bigger than 90 degrees. So you go back to the protractor. Anything like that's an obtuse angle. That, and you don't have to have the protractor. You can see that's got to be an obtuse angle, right? An open angle. So what is an acute angle? Smaller than 90 degrees. So when you get these sharp angles, right, these are acute angles. Sharp ones. Obtuse and acute. I would say it would be wise to commit those to memory because we will be using those in perspective. Okay, two more. These will be the last two. One of them is intersection. What is an intersection? When two lines do what? Cross each other, not meet. That's the intersection. An intersection will happen whenever there are two lines in any position except what? Parallel. If they're parallel, they'll go forever. But if you tip one way or tip one the other way, and they're infinite lines, they've got to hit somewhere. Any two lines that aren't parallel, somewhere they're going to intersect. They're going to cross through each other. Okay, there's something that's a complementary to intersection, and it's called tangency. Or we'll just use the word tangent. What is a tangency? What happens when you've got something that's tangent to something else? It's where two lines meet? No, because two lines will intersect. Even if you've got two lines that are like that, and that intersection is going to be kind of spread out over here, there's still an intersection. So what's a tangency? It's where a curve, presumably a circle, touches a line. So when you go like that, that's tangent. Okay, that's important in composition as well. You avoid tangencies in compositions. Slade had tangencies in his composition. They create tension. Sometimes you use them deliberately to create tension, but you have to watch out for them. But there's an application for this in perspective, which we will get to later. Now, this week, memorize those terms. Because if I'm talking and I say a word, like that's an acute angle, and you think, okay, acute. Now, by the time you remember it and get in, that's what happens. Where was he? And you tune out to try to remember the word. When I say acute, if you can think like that. When I say, obtuse. It's been a long time. Think acute, obtuse, and do that. It wouldn't hurt to do that on the paper a few times so that you just get a picture click in with the word.
So, is obtuse and acute does fit into oblique?
Yes, both acute and obtuse angles are oblique. They're oblique lines. They're oblique to each other. Aren't they weird words? I mean, they aren't when you've been using them for a long time, but any word is weird. If you say any word over and over and over and over and over, it turns into a weird word. Kids like to do that. Okay. Now, granted that you got those terms, I'm going to give you 5 more terms here. But these 5 terms are more like, how do you do perspective? What's the trick? Those were terms. This is more means to creating the optical illusion. I'm going to give you 5 means of creating the illusion. Let me get these up a little higher. The first one is, it is a law of diminution. Diminution, same root word as diminish. It means that as things are closer to you, they seem bigger. They aren't bigger, they just seem bigger. As things go away from you, as my 3-year-old said, that when the airplane flies away, it gets smaller and smaller. I don't know whether he even really knows that it doesn't get smaller and smaller. But as things move away from you, they seem to get smaller. So, if you've got 2 volleyballs, you can look at that and immediately assume this one's closer to you and that one's further away. The law of diminution. There is another law. The law of foreshortening. Foreshortening. We don't know what that is. I told you a volleyball. We don't know that it isn't the end of it. We don't know that these aren't 2 pencils. How could they be 2 pencils? Looking down on the eraser end. That is, when you look at a pencil, let's do it the correct way. Let's say that the pencil is something like this. Let's make it a stubby pencil. That pencil is not foreshortened. If you start to tilt it like so, because it's a cylinder, you're going to begin to see what? An ellipse as it tilts towards you. And because of diminution, as that goes away from you, see, that's going to appear to get smaller. It's actually convergence, which we'll get to in a moment. There comes a point where that tilts all the way on its end, and we don't know what it is. We're looking down on a circle, and it could be anything. Really, it's a flat circle. So foreshortening is the fact that things, when they are tilted on their major axis, appear to grow smaller. It's the strangest thing. It's logical, but it's really weird. So how would you know that was a pencil? Well, if your eye is anywhere in here, if your station point is right there, you won't be able to tell, except by the color perhaps. But if your eye is over here, you're going to see a little of this one coming over this way, right? So you might see something. Maybe I should do it over here. If your eye is right there, let's say that you're going to see something happening like this. And you might be able to figure out that that is a pencil. Just doing the lines. Of course, if we shade it and color it, that will help. It's something going away in space, cylindrical. That's the law of foreshortening. It applies to everything. It applies to your nose. kids draw a side of a nose at one point. When they're drawing the side of a face, they'll draw the front of an eye. Usually they'll start out doing 2 nostrils, but there comes a point if it's easier to draw the side of a nose as they get a little older, they'll draw a face from the front and they'll put a side nose like that. Because they don't know how to foreshorten. Okay, there's another law. The law of convergence. The law of convergence is the same as the law of diminution, except that it's more specific. I told you that if those are 2 balls there, you know, or you presume, that that one is further away than that one. That's because it diminishes as it goes back. But how does it diminish? Well, railroad tracks make the point very well, or even that pencil makes the point very well. If this line on this side and this line on this side are parallel, if these lines are parallel, which they are, when you tip them back in space, they do something tricky. They converge, which means they come to a point at a specific place, vanishing point on the horizon line. That's why that triangle, like that, becomes railroad ties, or a railroad track as soon as you do something like that with it. You know that they don't actually do that. They're parallel. Tip them back, they look like they converge. That's another trick, another means of creating the optical illusion. 4th one. This one everybody learns at an early age. Overlapping. You look at this and you presume that that is smaller, or excuse me, that that is further away than that. But you don't know, because you don't know what they are yet. So how will you find out? There's a way to find out. If you scoot this one over here, and it does that, then you know that the smaller one is closer, and it's a difference of size. Because, of course, when you first see that, you were expecting that was going to happen. Overlapping is a great one. It's good for composition, too. You use it a ton on the human figure. You know, the way you make a deltoid look like it's in front of that bicep, the way you make a bicep look like it's in front of that deltoid, you do that by reducing this to simple shapes and then starting to make one line kind of wedge into another. That's the way you make a forearm look like it's in front of an upper arm and a knee look like it's in front of a lower leg or in front of a thigh, depending on whether it's coming forward to you. Reduce it to simple shapes, and that overlapping, and then you start to kind of chisel at it, will give it a 3-dimensionality, an illusion of space. One more means of creating this trick. It's called aerial perspective. What does that mean?
Looking down at it?
Nope. That's 3-point perspective. That's convergence. Pardon?
You're above it?
Nope. I can see how you would deduce that, but that isn't what we're talking about. Yes? That's right. It means that air has some kind of substance to it, which means that if you are doing a pencil going back in space like this, you have to, if you really want to, I'm overdoing that a bit. If you really want to make that look like it's going back in space, imagine it one block long, and it's a foggy day. Do you get the idea? That means that what's going on up here, the color is going to be what? Brighter. As it goes back, that yellow will be different than that yellow back there. Okay, it'll dull down as it goes away from your eye. Okay, it means that details will be, what did you say? Blurrier. Crispness will be saying, I'm right up here, and then as things go away, they're harder to focus on. And so they will be blurry. It means that contrast will be what? From here to here. Light and dark contrast will be what? Softer. What did you say? Yeah, less contrast. That is, if you've got a chrome let's say you wrapped a chrome band around there, okay, to make this point. If you've got this chrome part holding the eraser, and you've got a real sharp white highlight against a real sharp black core shadow, you'll have the same thing there. It's going to be reflecting the same thing, but you will not let that be white, and you will not let that be black. You will make that white highlight a little grayer, and you'll bring that black highlight up so it's a little grayer, because it will compete with that, and if you want it to go, you'll make it so that as things change in space, they will change in value, that's contrast, in intensity, that's color, and in clarity, that's the sharpness of the detail. The 3 C's, what? Color, contrast, and clarity. They'll change in those 3 ways. Those are the tricks. Those are the tricks of creating the 3-dimensional illusion. Now I'm halfway done. Going to develop this a little further. How do you learn to get good at this? How do you learn to get good at that stuff? I gave you a hint of it last week. I gave you more of a hint of it with this overlapping business. You have to think in terms of simple shape concepts. I'm going to put the word concepts in there because they're ideas. I mean, this is chalk on a board. That's all it is. It is not a cylinder. This is not a cylinder, but it's the idea of a cylinder. So you have to think in terms of simple shape concepts. Now, what can't you build out of Legos? I mean, maybe you can't build love or anger or ecstasy out of Legos, but you can, out of Legos, build a couple embracing or 2 people beating each other to death. Anything that exists in space you can build out of Legos, or a reasonable facsimile of it. And if they had cylindrical Legos, which I don't know that they do, but if they did, then you could build anything. I mean, if they just got the little square ones, it means that to get cylinders, you got to work real big, and you got to have the little jagged edges that you kind of throw your eyes out of focus, and it'll look like a cylinder. But think about this. That means that if you can draw a little Lego in any shape, right? Legos are a basic, simple shape. That means you could draw anything that exists in space, theoretically. Well, that's why we care in a perspective class. We spend the whole semester learning to draw this and the cylinder and the sphere, because those are the things that you can build everything, and then variations of them, like a cone. If you can draw those simple shapes in any position, you can draw anything that exists in space, including smoke, because smoke has a shape to it, and hair has a shape to it, and whirlpools have a shape to them. That if you can understand those simple shapes, then you can start to see the simple shapes in all of the organic stuff out there and render it, put it onto the paper. That's called form. Okay, so you look at this, that's the form. We're drawing the form of a cylinder. That could be a Campbell's soup can. That could be the filter of a cigarette. That could be a chunk off the end of this. It could be all sorts of things, but we call that a cylinder. Now, if that was a pencil, if that was a cross-section of a pencil, that would not be the proper form of a cross-section of one of your wooden pencils, because they have things like this on them. Don't they become polygons? Right? I don't know how many there are. And then you have these lines. So it's not going to be exactly the same. It's related to the cylinder, but it's a variation on it. You get the idea? We're drawing the form. We're analyzing the planes. That's why if you've seen, there is a plaster sculpture in one of the rooms. This is not it. But have you ever seen the plaster sculpture of the head that is just planes, has the details left off of it? You know what I'm talking about? Where it looks something like this. When you go where? Oh, do they have those?